Okay. Let's go ahead and pick up where we left off. Look about right. Okay. So a couple of concluding ideas here. Most have this particular slide done. So what I wanted to talk about was, so we talked a little bit about the structure of the hydrocarbons, right? The fact that carbon forms 4 bonds with anybody, really. Doesn't matter who. It's not picky. And so as long as you satisfy the octet rule. But the important thing to always remember is this little idea here, right? So whenever you have a carbon hydrogen bond, it's an energetic bond. So there's an energy in there. And the question is, how do you know that there's energy in there, right? So if you were to sit here and say, okay, hey, propane, because it's got a lot of carbon hydrogen bonds in it, has a lot of energy in it. So if I don't really know anything about propane, how would you prove that to me? What would you do?
Set it on fire.
Okay, so set it on fire, and then what would happen? Right? So, or like the same thing you could do with like gas, right? So octane, so just basically light a match to it, right? Nothing. No, the freezing temperature for these guys is like abysmally low. Like you're not going to want to be alive at that temperature. So it's like really, really low. So the chances of finding solid propane is not likely. That's the reason why it's a gas. Because even getting it down to a liquid is a trick. Forget about getting it down to a solid. Okay. So there's a couple of things we want to take a look at here and sort of unpack in terms of the energetic spectrum. And hang on to your little experiment that you did, right? We're making things go boom. It's always fun, right? When you get to blow stuff up. So I think there's entire cable channels that just blow stuff up. So there's a couple of ideas. The first one is the first law of thermodynamics. Anybody know what that law is?
Water can neither be created nor destroyed.
Not matter. That's similar, right? That's conservation of mass. This one is similar. This one's energy. Yep. That's energy is neither created nor destroyed, only transformed. Now, of course, if you toss in Einstein's E equals mc squared, one can make a physics argument that there's really no difference between matter and energy, because matter can be converted into energy and vice versa. So you can make that argument. That's a physics argument. That's not our argument. So there is justification to say that the first law of thermodynamics and the law of conservation of mass in chemistry are essentially 2 versions of the same law. But this one we're talking about energy, right? So now what does that mean then? So imagine that I'm blind. I can't see anything. And you're trying to prove to me that this propane thing has a lot of energy into it. So when you do your little experiment and you light your match, explain to me what you're seeing. Okay, explain it to me. That means nothing to me. Okay, explain that to me. Hot. Okay, that's good. I'm blind. I'm not dead, so I could probably feel that, right? There's a lot of heat there. Okay, what else? Keep going. So you can smell it. So that's usually like
Yeah.
the debris from what you're burning, like carbon from wood or something like that. What do you mean orange? So that's okay. I like that. That's so let's just stick with the orange one. So it's orange. Okay, but I like oranges. I'm told, because I'm blind, remember, that oranges are orange. So are you trying to tell me that you got a bunch of oranges that are hot? I'm trying to put an image in my head from how you're describing this to me. Transparent and wavy. Okay.
Burns.
Okay, that would be heat, right? You guys are missing, you're like dancing around the obvious. You're overthinking it. You're like way overthinking it. Beef. So oranges, I'm back to oranges again, right? What's the fundamental property of it? And don't just think about propane, think about anything like this.
Oh, smell.
So smell, but use a different sense. I hope you're not tasting it. Okay, heat. You're missing your dominant sense. You walk into the room and it's dark. And in the fireplace is what? Who said that? Light. Right, that's why I said you guys are dancing around the obvious. You're describing the color of the light, but the answer is not the color, the light itself.
Right. Put this up as blind.
Yeah, well, okay. So you're not good. Well, you can still describe it. That's where the transparent was. So I was trying to get that out of you. But even if a blind person will have some concept of light, even though they can't see it. Right. Yeah, because you can, right? Because you can see variations in the darkness, depending on whether or not your optic nerve is fried or whatever, right? That depends on that one. But so here's the thing, right? So okay, so this is great. You're describing this to me. So the two dominant things that I heard was heat in various forms that you said, right? And light in various colors. So what does the law of thermodynamics say? That basically says that all of the energy that's built up in this bond has got to equal all of the energy that's coming out of it. So when we light this thing on fire, we feel heat and light. And that basically means that this has to equal 100% of the energy that's to be found in those bonds. So if you want to know how much energy is in the bonds of a carbon-hydrogen bond, light it on fire. The amount of energy that you experience, heat and light predominantly, is equal to how much energy was pent up in those bonds. Think about that for a second. That's like a crazy ton of energy in that little itty bitty bond. Oh, let's do another example of this idea of energy transformation to kind of get an idea of what we're talking about here. Probably the most mind-blowing explosion of energy, literally and figuratively, that we've got access to, right? The mushroom cloud. So if you want to know how much energy is pent up in an atom, take a look at a mushroom cloud. No, not a picture of one. Like take a video, like look at one of the old like videos of when they detonated, like Bikini Island is a perfect example, right? Because here you have this little tropical island. I don't know why they picked this poor little island. I think it's like, right, you have palm trees everywhere. And then all of a sudden, what do you see? This massive mushroom cloud, right? And it's not even that. I mean, it's eerie. I mean, it's creepy, right? Because you can't hear anything. All you see is this mushroom cloud going up, and then you can see and watch it closely. Don't just look away and say like, oh, that's really cool. No, 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 no. Like, study what's happening. Like, look at the mushroom cloud. Look at those massive waves of shock that are rippling throughout the entire, like an entire area, like Denver would pretty much be evaporated essentially, right? So it's basically just rolling out. And it's like, and there's some really great images where they put up dummy ships offshore, and you can actually see the shock wave hitting those dummy ships, and they're basically capsizing. I mean, and this is like miles away from the epicenter. And so when you take a look at that massive mushroom cloud, that is basically the energy associated with what's inside the atoms of that original material. So just to kind of give you a little bit of a kind of a nuclear physics 101, the bomb building 101, right? Use the simplest version of the bomb. There's different versions of bombs now, but the simplest version of the bomb that they dropped on like Nagasaki and Hiroshima, right? Fat Man and Little Boy, that they named him, because that's what they did back in those days, right? Yeah, they do all sorts of crazy stuff. Yeah, you just let the pilots and the soldiers go crazy. It's like whatever you want to draw, right? We're just blow people up with it, so just do whatever you want. So I guess it's like a macabre sort of gallows sort of frat boy release of stress, which I appreciate, because I mean, if I was getting shot at for a living for most of half a decade, I would probably be a little, really I'd be releasing a lot of stress myself. Right, but basically what happens, the way you get this thing to blow up is radioactive material is not generally explosive, right? I mean, in nature, it's unstable. We talked about its instability. And generally what it likes to do is it likes to radiate over time. It likes to sort of leak out, essentially, until it sort of gets itself stabilized. However, in radioactive physics, there's a phenomenon called critical mass, right? And so many of us know that term, right? But most of us probably don't understand what it actually means. Critical mass is a nuclear physics term. And what that means is that when you have two radioactive materials, plutonium, for instance, or uranium, which are usually the bomb maker's preference, right? Generally speaking, if it's pure enough, and that's one of the reasons why when you take a look at like nuclear enforcement policy, where we're trying to keep third world crazy countries from getting nuclear weapons, we're interested in their refinery process. We're not interested necessarily or worried about them having access to uranium because it's natural. We're interested in their infrastructure to be able to purify the uranium to weapons grade uranium. And so if it's pure enough, then what'll happen is if it reaches a certain mass, it'll get so unstable that it'll just go complete chain reaction. That's mushroom cloud territory. And so what they did with the bombs was they took two subcritical masses and separated them with some sort of a mechanism. And then what they did was upon detonation, they removed that barrier so that those two masses came together. And when they came together, they reached critical mass. They became unstable enough together as a group that they just basically went catastrophic. And that's the nuclear bomb. So when you take a look at a mushroom cloud, like what hit Nagasaki, Hiroshima, you're talking about the energy of a piece of mass that's maybe about that big. So that's kind of mind-blowing, just how much energy you're talking about. Okay. And the same thing can also be true with the carbon hydrogen bonds. So that's a good thing for us, right? Because when we're talking about our big biological questions of life, one of the first things we have to lay down is that energy foundation. We need an energy strategy. This is kind of where it begins, right? So now all of a sudden, we know we need energy, but the question is, okay, where are we going to get this energy from, right? And not only that, but even if we get energy, we have to get it in a usable form, right? We have to be able to use it. I mean, it doesn't do us any good, if wood has energy in it, if we can't digest it and make use of it. So it's kind of like inaccessible for us. So it might as well not even exist. So energy from the sun, which is free, is great, but it doesn't do us any good, right? I mean, all it does is just tan us up a bit, right? And we don't get anything from that. So there has to be a way that we can get access to it. and then we can use it. Well, this right here represents exactly that, an accessible form of energy. Why? Because all of our biology and our chemistry, we learned this from chapter 2, right, is wrapped around this idea of being able to set up chemical reactions so that we can get the things we need, including energy. So if we've got energy stored in this carbon-hydrogen bond in a chemical form, then that means we potentially could tap into that energy and fuel whatever processes we need to fuel. Yeah.
This might be a stupid question, but in terms of like when the sun hits the solar panel into energy, is that a like chemical reaction, or is it a change in the state of from the sun?
It's not a change in the sun itself. Generally speaking, we were talking about solar technology. There's a couple of versions of that. Most of them is kind of a knockoff of something the plants already do and have done for quite some time now. Yeah, because that's part of what they're doing. They're trying to capture that energy in a usable form. In our case, instead of making molecules with the sunlight energy, which is what plants do, we basically create a capacitor that has the ability to store up the energy. So we absorb the sunlight energy, and then we convert that energy into sort of an electrical form that will then kind of store it in a capacitor, and then that basically kind of moves it through the cell itself, and we're able to use that energy. So it's kind of like a little like it's based on the same principle as what we saw in chapter 2 when we talked about electrons being able to absorb energy and jump up to their highest energy state. And so there's always a little bit of that in there, because then once you actually get an electron that has a higher energy level, then you can move that energy through a system of, or in this case, a series of electrons through like a copper wire. That's basically would be our electricity. Does that make sense? And so that's basically, so all our solar technology is actually just it's a ripoff. It's a ripoff of what plants have already set up and have going for quite some time. So now that's kind of gives us a sense of the energetics, right? Which is helpful, because now not only do we need an energy plan, but now we've got a source of energy that we can actually form and build our energy plan around. Okay, so that's really great. But we have these hydrocarbons, right, of varying lengths, these chains of carbons. And remember, these chains can form all kinds of different looks. You can have them as long as you want, as short as you want. You can connect these guys in rings if you want. You can fuse these rings together if you want. So these carbon backbones can be any construction that you want. But here's the thing. At the end of the day, they're all carbon backbones, right? They're all carbon hydrogen non-polar molecules. So the question is, how can we sort of get more function out of these things other than just like light it up and go boom, right? That's helpful in some sense, but I mean, really not for us, is it? I mean, if we're lighting all of our molecules on fire and they combust, I mean, we're just basically gonna be a walking torch. Right? That's not really all that functional. So how is there a way that we can harness this molecule, tame it, so to speak, right? And add different features and functions to it that will allow us to be able to do more with it. And the idea of that is what is revolving around this concept of functional groups. Functional groups will actually be able to give this carbon backbone different types of chemical capacities. Now, what I want to do is I want to use an analogy. I want to go sort of holidays on you, sort of classic Christmas sort of holiday sort of a thing. Because I mean, most of us, if we've been around for a while, in the business end of a Christmas tree here or there, right? Pictures of them. Even if we hate Christmas or we don't celebrate it, you've still seen it. So you can't escape that one. But you've probably seen enough of these things, right? Like, especially in New York, because they're everywhere. The department stores have them all up, right? There's Rockefeller Center. Every city has some sort of a Christmas tree or whatever. But you've probably been around it long enough to know that not all Christmas trees look the same, right? And actually different Christmas trees will have quite a very different effect on them, right? So at the heart of it all is just a tree. Now, sure, you can probably vary that tree. Some people like the Doug fir, some people like pines or whatever. I mean, if you're like a tree nerd, I mean, it's like, no, I got to have this particular type of tree. But at the end of the day, it's a tree, right? Just like a carbon backbone is just a tree. Now, are there different types of carbon backbones? Sure. They can be long, they can be rings, whatever, just like it could be Doug fir or a pine. But at the end of the day, what you've got is your base. It's a tree. Now, Christmas trees, to make them do different things for you, to sort of send different messages, don't vary by the fact that they are a tree. They vary by what you put on the tree, right? So it's the way you decorate them that makes them different. So you can make a very cold Christmas tree, right? Wintry cold, and like decorate all in white, right? And that would kind of a very sort of wintry sort of a cold effect. Or you can make one that's very warm and cottagey feeling, like a Thomas Kincaid picture, right? So it's like dark reds and gold, right? Kind of like the whole fireside sort of a thing. And that's kind of all this sort of old world kind of cottagey sort of a feeling. Some families that I know of that are interfaith, they do like a Hanukkah tree, right? They kind of a fusion of the two. They do Hanukkah and Christmas. They celebrate both of them. And so they kind of do like a blue and white theme on the tree. And they've got, you know, in some cases, at this one particular family, actually, they burn through a lot of candles, right? So they got like the Advent candles and they've got the Hanukkah candles going on. So there's a lot of candle burning in this particular family that I know of, right? But that's a very specific type of a tree. It's very different than say what you would find in Rockefeller, right? You've probably gone to cause-related trees where they're decorated with different types of donors. Like if you're donating to a charity, and they'll set up a Christmas tree and they'll be like, okay, here you kind of donated to this charity, and so now you kind of got an ornament on the tree as sort of a way to sort of display the activity of donation, to try to get donations that time of year. So different trees are different, but they only differ by what you put on them. Just like carbon backbones are mostly all the same, but we can get them to have very different types of functions by the ornaments that we hang on these carbon backbones. What are those ornaments? Functional groups. Now, since we're kind of going through a little bit of organic chemistry, because we're dealing with an organism that's primarily carbon, that's what you are, and that's the field of organic chemistry, studying carbon-based molecules, then we're going to study some of these ornaments. Now, in organic chemistry, especially in OrChem 2, basically what you're doing is going like functional group by functional group, and you're learning the entire pantheon of all the reactions associated with that functional group. And we're not going to do that. We're just going to do like a little introduction of what the functional groups are and how they give us biological capacity. Okay, let's start with the first one, the hydroxyl group. So the hydroxyl is a molecule that basically where you have an OH together. Now, this is a package deal, right? The important thing about functional groups is they're a package deal. So this OH is not separate. It's not oxygen and hydrogen. These guys are together. They're joined at the hip. They don't get separated, generally speaking, right? So that's what these functional groups do. And generally speaking, any carbon chain that's attached to an OH is basically how this would look. Now, what I want to do, and by the way, a couple of things, first of all, by way of definition. I put this letter R in there. Now, that's an organic chemistry thing. And what organic chemists do, like when they're looking at functional groups and they just focus on the functional group, they don't care what the rest of the carbon chain is, then what they do is to denote some whatever carbon chain it is, they just put the generic term R. So whatever your carbon, it could be 2 carbon, it could be a 3 carbon chain, it could be a 20 carbon chain, it could be a carbon ring, whatever you want, right? So whatever carbon chain is out there, we don't care, we call it all R, because we're just looking at the functional group. Okay, so that's what R means. So let me give you a specific example. Let me draw this guy right here. What is that? It is ethane, yes. So this is ethane, a hydrocarbon, right? You like this, it goes boom. Now, if I take one of those hydrogens and I swap it out for a hydroxyl, then what I've created is ethanol. So the suffix in organic chemistry basically betrays the molecule you're using. So anytime you hear the term "ol" on the end of it, methanol, propanol, isopropyl alcohol, right? Isopropanol, those are all alcohols. Basically what happens is you put an OH on there. So now, here's my question. Go ahead, Christopher, go ahead. Question?
Does the R change in any sense?
No, in organic chemistry, it's just a generic placeholder. So it's whatever you're attached to, whatever that happens to be. So if I were to ask you to go out and get some ethanol and bring it back, what'd you guys come back with? Ethanol. If I asked you to go and out and go bring me back some ethanol, what would you guys come back with? What? Not a gas. What?
Alcohol?
Yeah, right. The stuff that we all drink. And in its purest form, like moonshine, right? I mean, the hardcore stuff. But basically everything that you guys drink after exams, right? So as of after Thursday, my guess is after class on Thursday, you guys will probably go across the street and do your pub crawl. Try to drink away the memory of what just happened.
Friday.
And
Different story.
not Thursday, but Friday, you're gonna let it all go. Okay. So nice. Yeah, don't drink alcohol at bathtubs. So it sounds like a pub in here, right? So we're already ready. All we need are the beverages. As soon as I say ethanol, you guys are like, yes, please. Let's just go ahead and just break. So that's an alcohol, right? So you go from, yeah, you're more of a tactile learner, right? You learn by experience. So it's like show and tell, right? You got to have enough for everybody. A demonstration, right? So here's some ethanol. So basically, so notice what happened is we transformed from ethane, which is a hydrocarbon and poisonous, right, to ethanol, which you can drink. All because of that one little functional group. That's it. So these functional groups actually pack a pretty powerful punch in terms of dictating the chemical overall personality of these carbon chains. Okay. Now let's go to another one, carbonyl. The carbonyl is basically characterized by a carbon double bonded to an oxygen. And I'm not going to put R's because for a very good reason, because there's two different types of carbonyls. The first one is called the ketone. And this one is a situation where you have an R group comes into the carbonyl carbon, and then the R group leaves. That is to say the chain or the backbone will come into the carbonyl carbon and then will exit. And so I like to use propane. So here's our propane here. Let's say that we make this center one a carbon double bond. The rest of it is all just bound to hydrogens. Okay, so I'm not going to write them in just for sake of simplicity because I only have a limited space. But if you do this guy right here would be called propanone. Notice the ONE suffix is what betrays the ketone. So notice you have the carbon chain coming into the double bond, the carbon chain going out of the double bond. Okay. Well, now what happens if we move this carbonyl to one of these end carbons instead? So what if we did something like this? And then it would terminate there. There's a hydrogen. This would be propanal, Al. This would be an aldehyde, as in formaldehyde. This is basically where your R chain comes into your carbonyl bond and terminates in a hydrogen. Now, why are these important? Because I want you to know what ketones and aldehydes are. No, for one very good reason that it was actually powerfully illustrated to me in organic chemistry in one of my favorite labs, actually. And just to kind of understand what organic chemistry is like, is in organic chemistry, basically what you do is you learn all these reactions that these molecules go through, these functional groups go through. And then when you get into the lab, you basically try to synthesize these things, right? So you try to actually set up this chemical reaction and you try to make something, right? Now, the problem with that is most of what you make is clear, odorless, and doesn't have any color to it. So you don't really know what you have when you do a synthesis in organic chemistry. That's the reason why when you make something or you get something, and in organic chemistry, lab is really fun because this is the one lab where you feel like a mad scientist because you got like all these like round bottom flasks and all this tubing going on and these little condensers and these catch chambers. And it's like, you really do feel like a mad scientist a little bit. And you kind of get this like little drip of solution that your product that you got. And then you have to go analyze that to figure out what you have. And so there's like all these different instruments like magnetic resonance and infrared spectroscopy that helps you sort of understand, okay, I got something, but what did I get, right? Did I actually get what I got, what I think? And so there's a lot of that endpoint analysis, and that was a lot of organic chemistry. Except for this one lab, which I loved, because in this lab, we were working on the carbonyls, and what we wanted to do in this lab, we wanted to synthesize two molecules. One was cinnamaldehyde, which smelled like what? Not a trick question. Cinnamaldehyde. And then the other, which is a ketone, but we affectionately called it by its nickname, banana oil, which of course smells like bananas, right? And I love this one because we didn't have to do any after the synthesis because you knew when you got it. The second you got it, the room just filled. And then once you got banana oil, filled with the smell of bananas. So this is it's funny because in this lab, you think we were cooking, like baking in there, because the whole room just like smelled of bananas and cinnamon. I loved it. Of course, you had a little bit of aromatherapy going on in there. And I mean, who already doesn't love bananas, right? I mean, that's a primate thing, right? Pretty much all primates will go for a banana. But there's a couple things. Now, obviously my chemistry friends were getting their nerd on because they're like, oh, that's really cool. Let's go ahead and analyze the structure anyway. It's like, for me being the bio person, I was just like, sort of just taken aback by the biological implications. Because here was an absolute powerful illustration of the interaction of organic chemistry and biology. How so? The scent of cinnamon, which is a real thing, right? It is a real organism in the world. It's a biological organism. That scent that is very popular, especially during the holidays, right, is an aldehyde. It's action to us as an aldehyde. The smell of bananas, which is arguably probably one of the most popular things, especially in babydom, right? I mean, it is like the #1 seller in baby food. If you want your baby to eat peas, you mix it with bananas, right? I mean, every mother kind of, it's like, okay, you won't eat any of this, but you'll eat the bananas, right? So I'm going to mix some of this carrots in with the bananas. And so anything banana will make it all go down, right? When you're feeding a baby. But that smell is a ketone. So the backbone of fragrances in nature is basically resting on ketones and aldehydes, which is cool, right? Because that's organic chemistry in real life, looking at fragrances. Now, why exactly then do you have fragrances? That's another interesting biological application. Why? Why do we even have a ketone that smells like bananas? Why do bananas care to make a ketone that smells like bananas? So we can eat them, right? Think about this for a second. When you have fragrances like today's Flower Day, I mean, we're going to make a run on plant sex organs all day long. That's basically what flowers are, right? But when you see a plant or a flower, what is our natural response to it?
Smell it.
Right? We want to smell it, especially if it's one of those hot days and you can kind of already get the wafting fragrance of the flower in there. You're like, something really smells good. And what do? You stick your nose in there, right? Roses are particularly good for this sort of thing because they're like perfectly shaped to like just sort of like open up the center of the rose with your nose as you're digging it down in there. And it just sort of like kind of just hangs onto your muzzle, right? Just gently, just sort of hangs onto it with the petals and just kind of sticks it all in there, right? And you're getting a good smell of it, right? But then what do you do? For those of you who have allergies, you're like freaking out, right? Assuming you're not allergic to it, right? Then what do? You see another flower right next to it. And you're thinking, wow, you're kind of pretty too. And then what do? I want to smell this one. As soon as you stick your nose down into that one, what have you done? Yes, you've been used. You've been totally worked. Flowers are out to get you. It is true. You've been totally worked over, dangled around like a puppet.
How many people use them to apologize? I think they deserve to use this every once in a while.
They've been using us from the dawn of time. Matter of fact, one would argue that we think we're the dominant species, but plants have, I mean, we are like the lap dogs for plants, doing their bidding. They're lap dogs too, all animals. All animals are lap dogs. Oh, but it gets worse. Let's go to the banana, right? Every primate takes a look at a banana and is like, what? Ooh, look at you, all nice and bright yellow. Well, guess what? Why do you think the banana made its fruit bright yellow?
Stands out.
Yeah, who's it standing out to?
Those who didn't see the colors.
Yeah, the dumb primates on the ground who are getting worked. So what do? We go up there, we grab it, and then we're smelling it. And what does it smell like? Ooh, this smells wonderful. Oh, wait. But why did it make a wonderful smelling ketone?
So the
Because it wants us to do what?
eat it, eat the seeds, and then distribute it later.
Bingo, right? So we eat the banana, which, by the way, bananas have seeds, not the ones you buy in the store because we cultivated them out, but real bananas, wild bananas have seeds in them. All fruit does. That's what fruit is. But the reason why fruit is attractive and smells good and colorful is so that us color seers, especially mammals, will lumber in there and be like, oh, hey, look at this. This smells great. And it's soft, right? So I can chew on it. I can swallow this thing without even worrying about it. This is awesome. And then what do? You go puttering down the trail in the jungle, take a dump, and then you've spread the banana tree's seeds to far-flung areas so that they can conquer the world, one dumb primate at a time. So yeah, we're totally worked. So who's really the master of the universe? Absolutely. You'll never see a banana the same way again. So yeah, but the only reason it supplies with energy is because it knows that we want it. So the reason why it packs sugars into there is because they know that we have a taste for sugar. So everything that plants do when they make fruit is purely to entice us sugar-loving, visual, smell-oriented mammals to eat their fruit. It's almost kind of like that witch with the apple in what is that one? Yeah, right. It's like, here you go, dearie. Right? It's like that's the plants, and we take it, right? And we eat it happily, and it tastes yummy, and we eat it again and again and again and again. But yeah, don't be delusional. We don't own the world. We're owned by the world. Don't be delusional. We're not that special as mammals, anyway. That's very depressing. That's very anti-humanism right there. Yeah, good. Ours is a generic backbone, carbon backbone. Okay, now let's take a look at a version of the carbonyl, the carboxyl. So the carboxyl basically will have an R group, and then it'll have your carbon double bond. But now instead of either an R group or a hydrogen, what will happen is it'll terminate in a hydroxyl group. So this whole thing goes together. This is all a package deal. It's oftentimes abbreviated as COOH. And the reason why this guy is called an acid is because this H can be donated. Remember, that's what an acid does. It dissociates and it gives off a hydrogen ion, which is what causes the acidity. So this guy can actually toggle back into this particular form, and it can go back and forth. Okay, so this would be kind of like it's acidic form. So it's basically given an acid, or it's given that hydrogen up. So it's basically created acidity in that case. So those are your carboxylic acid. I like to sort of compare these with the next group, which is the amino group. The amino group is going to have an R group tethered to a nitrogen, but then also tethered to two hydrogens. So this is your amino group. And what this forms is the backbone of the amino acid. I'm going to basically take a look here at the amino acid. First of all, in the amino acid, you're going to have a nitrogen, so an amino section. That's where the amino portion of the amino acid comes from. You're going to have a central carbon, which has a hydrogen on it, and then it has an R group of its own. But there's 20 different versions of this R group. We'll learn more about these when we get into amino acids in the protein section of these 20 different types. And then it's going to be terminated by a carboxylic acid. So this is your acid group. So all amino acids have this backbone in common. The only thing that the way they differ is with these R groups. So they have, like for instance, if this R group here was hydrogen, it would be glycine. In this case, they use an example of alanine. That R group is a methyl group. So it's a CH3 group on there. Okay. So different side chains will give you different amino acids. And that's what you have to work with to build your proteins with. And we'll talk more about amino acids and take a closer look at them once we get to that section. The next one is called the sulfhydryl. This is basically an R group that has a sulfur. It's like a hydroxyl, only now instead of oxygen, it's sulfur. And this is important because you find this in proteins, specifically in the amino acid cysteine. So you can see how you have this SH group in this R group. So its R group has a sulfhydryl group in it. What this does for a protein is where most proteins are folded together and held together with hydrostatic interactions, with hydrogen bonds, right? So they got hydrogen bonds between polar side chains. They got hydrophobic interactions between non-polar side chains. And so these are the weak interactions that hold proteins together, with the exception of the cysteine. What happens with the cysteine, and basically, by the way, what that means is because the proteins are folded together and held together with these sort of electrostatic interactions, polar, polar, non-polar, weak interactions between molecules that we covered in chapter 2. It means that proteins, when they fold up, are functional, but they can easily be unfolded, right? So if we add a little bit of heat in there to break it up, we can overcome those interactions, and because they're weak, and we can undo them, and that will kill the protein. With the exception of the sulfhydryl group. The sulfhydryl group, what will happen is when a protein folds, if it has two cysteines in close proximity to each other, it forms this is the only one that forms a covalent bond. This is a strong one, remember? This is not the molecular interaction. This is that strong one. This is the octet rule thing. And this is called the disulfide bridge. Now, what this does is it cross-links the protein and helps stabilize it so that it doesn't just come apart, randomly. It kind of has a little bit of stability there. So it kind of holds things together. It's not unlike if you're doing like sewing work. It's not unlike using the pins to kind of hold your material. Once you kind of have the material positioned the way you want it, and you kind of put the pin in there as a placeholder so that you can hold it so you can get the seam right. That's exactly what the disulfide bridges do. It's like you're kind of folding it all up, but you're using these disulfide bridges, these covalent bonds, to sort of hold that protein together to kind of stabilize it, so the rest of the folding can sort of work out the way you want it to. Never thought I would use a sewing analogy. That's the first time, actually. I'm proud of myself. See, I am able to do new things. But anyway, the next one is the phosphate. This one we tend to see in DNA and RNA, the nucleic acids. And so what this basically is, you have an R group coming, or your backbone coming in, and it's going to be essentially bound to a complex of phosphates and oxygen. So you have a phosphate in the center, bound to 4 different oxygens, and one of those oxygens is doubly bound. But these oxygens, because they're electronegative, have a lot of negativity to them, right? And so these tend to be associated, these phosphates tend to be associated with negative charge. And because they have a lot of electrons in them, because of the oxygen sucking all that electron density toward it, oftentimes also associated with energy. Okay. Typically, in biology, we always write the phosphate group as a P in a circle. Okay, that's our phosphate. Matter of fact, you'll never see me write out this whole thing. It's always going to be P in a circle. That's how you know I'm a biology person, not a chemistry person. Right? I always go for cartoons whenever possible. So the last one then we're going to take a look at is what's called the alkyl. And this is kind of a generic term. So this is basically where a smaller carbon backbone becomes a functional group. So let's give you an example here. I want to, I'm going to draw a backbone, and it's going to be a specific one. It's called benzene. And it's basically a hexagonal cyclic ring that has alternating double bonds. So this is a really, really like a big carbon backbone. And generally speaking, if I take benzene, I can attach different things to it. If I attach one of these smaller carbon backbones to it, then that carbon backbone becomes an alkyl, or becomes an ornament, if you will. Here's a good example. Let me add a methyl, right? So we had to add methane. So we're, instead of one, in that fourth hydrogen is going to be attached to benzene. So this would be like a methane. So this would be methyl benzene. Notice the YL. So I know that the methane is the smaller of the two backbones because of that YL ending. Okay. What happens if I put a propane? Propane's getting pretty big, right? Certainly that one has to be, no, it's not bigger than benzene. So this one becomes propyl, methyl benzene. Notice how organic nomenclature goes. It's very descriptive. It's telling you exactly what's on there. The root is your backbone. And then it's the front of it is all the stuff, the ornaments that are attached to it, right? So here we know we have a propane attached to benzene, and we have a methane attached to benzene. So it's propyl methyl benzene. In cases where there's different positions, you oftentimes will use numbering systems to say, you know, this is the number of the carbon that this particular ornament is on, this particular functional group is on. That's where you get to all these big, long chemical words where you have things like, you know, 1, 3, 4, 5, tetra, amino, methylene, diamine, hexamine, that kind of stuff. So that's describing where the position of where these functional groups are. And the idea is you got 4 of them, right? You have 4 of them attached to different carbons. So these are the main functional groups that we're going to be taking a look at, and that we want to keep in our radar. So you want to be able to be comfortable with those guys. Now let's take a look at isomers. So isomers basically are molecules that have the same molecular formula, but they're different, right? So here's a good example, C6H12O6. What is that? Glucose. But it can also be fructose, or it could also be galactose. Those also have C6H12O6, right? That means these guys are isomers of each other. They basically have the same molecular formula. Now, structural isomers basically differ in arrangement of atoms. So it's kind of structurally a different shape, okay? Stereoisomers basically only differ in 3-dimensional orientation. And the stereoisomer that I like to use preferentially is the enantiomers, because enantiomers make sense to us. Enantiomers are basically mirror images. So it's like your right and left hand, right? That's basically what an enantiomer is. It's basically your right and left hand. Your right hand is an enantiomer to your left, and your vice versa, okay? Now, stereoisomers aren't all mirror images of each other, right? So an enantiomer is a specific type of stereoisomers. So it is true that all enantiomers are stereoisomers, but not all stereoisomers are enantiomers. Let me say that again. All enantiomers, that is mirror images, are stereoisomers, but not all stereoisomers are enantiomers. That means there are other stereoisomers that are not mirror images, but they still have spatial variation in them. That makes sense? We'll see an example of that actually. So what does this give us, especially with the enantiomers? Well, what this gives us is this idea of right and left-handed molecules. So in this case, we have D sugars, that's just a designation for right versus left, and L amino acids left hand. Right, see these are left-handed molecules. Now, the thing with this is all of your body are left-handed. All the molecules in your body is left-handed. Because we only have left-handed enzymes. So what does that also mean? So has anybody ever gone to like Vitamin Cottage, right? Natural grocers. And you've gone into like the supplement section and you look at an amino acid, right? And you see the bottle. One says tyrosine, the other one says L-tyrosine. Have you ever wondered what they're trying to communicate there when they say L-tyrosine? Or have you looked at the bottom, you're like, what's L-tyrosine? Right, and how does it differ from just tyrosine? Well, here's what L-tyrosine. L-tyrosine is basically left-handed tyrosine. That's the amino acid that our body uses. So here's the thing, though, to always be aware of, and we run into this a lot, right? Whenever you make an amino acid, let's say we were to make tyrosine or any of these molecules, it's like making a quarter, right? But remember, when when you first make a quarter, all you make is a little silver disc, right? Now, can you make a silver disc that only has one side? No. The second you make a disc, by definition of its structure, you've got two sides, one side and the other side. It's not physically possible to make a one-sided tyrosine, right? You get both. The same thing is also true for these molecules. It's not possible to make a one-sided or just a left-handed tyrosine. The second you manufacture tyrosine, which is what these supplement companies are doing, you get both. It's like making the disc. You have both left and right in equal proportions, just like the disc, right? You have half one side, half the other side. So then what are they trying to tell you when they say L-tyrosine on there? Your eyebrows should go up a little bit. It's either a straight up lie. I would argue it's a straight up lie because they're saying one of two things that are both lies, right? The first one is, oh, we only make L-tyrosine. We don't make the right-handed tyrosine. Lie. That's like saying we only make half a quarter, not the other side. Well, you know, by definition of the reaction is that's not possible. So when you were supposedly making L-tyrosine only, you are making both in equal proportions. So that's one lie. Okay. No, because they're not connected to each other, right? You just basically make one and the other. It's like light and dark, right? Light has no meaning unless you foil it against dark, right? Good has no meaning unless you foil it against bad. In order to know what one each of them is, you have to have the other. One defines the other, right? So in order to know what left-handed is, you have to have a right hand. That makes sense? Because otherwise all you have is a hand and it's not left or right, right? So right defines left, left defines right. So you have both of them out together. So if you're saying you're only manufacturing left, you're lying. The other thing that I also raise an eyebrow to, you may not necessarily be lying, is that you're saying, hey, we've got a process. Yes, we're making both equal proportions. We've got an enrichment process. So we're able to identify the right-handed tyrosines, get them out. And so what we put in our pills is just the left-handed tyrosine. And typically that is a proprietary process. Anytime you hear somebody in a company like that use the term proprietary, shoot them. not literally, but figuratively, right? Because they're lying. Because here's the thing with proprietary. Proprietary basically says, everything I just told you is a straight up lie, but I want to hide behind this idea. I don't want to tell you that that's a lie. And so I hide behind the proprietary curtain. You know why? Because if it was proprietary, then they would have gone to the patent office, patented it, and everybody would know that it belonged to them, and they wouldn't touch it, and they would be able to make lots of money off it. That's what people do when they have proprietary anything. You have it patented so that you can own it and make money off it. Unless, of course, your patent is a bunch of BS. And no patent office is going to patent a bunch of BS. So what do you do instead? Oh, well, this is actually a legit process. So because we can't patent it. So we're going to say it's proprietary. So basically that's also a lie. So essentially what you're getting, that $60 pill that you're buying, half of it you can't use because you can only make use of the L-tyrosine. Good. Oh yeah, absolutely. The problem is there's the regulation on the supplement side of things is just so wild west that you're wasting your time.
You don't have to go through the FDA.
No, supplement. That's the reason why, if you take a look at it, and this is the thing that always pisses me off, because I kind of feel like there's a lot of really stuff in the supplement industry, but I'd say probably about 80% of it is largely just marketing and lies. That's all it is. And any kind of measurable effect is probably mostly placebo effect.
The best way to go about it is, they'll always have like the new products, but things that stay around since like the 80s. You know what I mean?
They haven't killed too many people. But that's the reason why we have the FDA, right? I mean, you have to be careful in the supplement industry because you can actually do yourself quite a bit of harm if you don't know what you're doing, which is one of the reasons why doctors have a problem with the supplement industry. It's not regulated. But that's what the FDA, I mean, for all of its sluggishness and slowness, I mean, they do a good job of making sure that our therapeutics are therapeutic and they don't hurt us. You can't say that for the supplement industry. The pharmaceutical industry would look a lot like the supplement industry if it weren't for the FDA. Basically, which is, hey, good luck. Go ahead and take this medication. It might kill you, but again, it might heal you, right? Does that sound familiar? I mean, that's what the snake oil salesmen were doing on the backs of wagons in the turn of the 20th century. It's the same basic thing. You've just basically blitzed it up a bit, give it some color, and added some marketing to it. That's pretty much all you've done. Okay, so what we're going to be studying then in this particular chapter is all the macromolecules, right? So we're kind of bringing, and there's still a little bit of organic chemistry because obviously we're talking about the organic chemistry. They're talking about the chemistry of the carbon-containing molecule. And we have 4 major types of macromolecules. This is what we're going toward. So if I were to take you guys, any living organism actually, and break you down into your macromolecules, there would only be 4 buckets. So every single molecule in your body is either going to be a carbohydrate, a lipid, a protein, or a nucleic acid. There's nothing else, okay? So those are essentially what we have to build our biological organism with. Now, how do we build this? Well, basically, we're going to use the brick wall analogy. How to build a macromolecule is like building a brick wall, where the brick wall represents what we refer to as the polymer. Poly means many, mer means things. So this would be our brick wall. Now, what exactly are those things? Well, those things are monomers. So mono means one thing. So this is basically the single subunit that builds the polymers. So what's the monomer for a brick wall? A brick, right? So that's our monomer. That's our secret. Every brick wall is made of a brick, multiple bricks, right? However, are all bricks the same? No, you got a lot of different types of bricks, right? I mean, the one you see the most is the common red, right? Your typical brick. I mean, we even have a brick red color, right? We even name after it. But if you've ever gone to like a landscaping center, you'll notice there's a lot of different types of bricks, a lot of different shapes of bricks, a lot of different colors of bricks. And so depending on what you want to do, you can pick and choose what types of monomers you want to use to build your wall. And your wall is going to have very, very different personalities depending on how you pick your monomer. So this idea of building a polymer brick wall from individual subunits, the monomer, is something that's consistent throughout all 4 of these macromolecules. So the starting point, if you want to build a brick wall, is to build a good brick, right? So that's what you want to do. We'll get there. But what I want to do, first of all, is kind of fill out the brick wall analogy, because we've got materials now, right? We've got a monomer. We can build a polymer with it, but now the question is, we have to add a little bit more to that to really understand it. This image here is for you table people. For those of you guys who like to have everything all in one place, this is essentially the rest of the chapter, all right here, just kind of in a table format. This is for you guys to organize your information. Remember, a lot of you guys have asked me, how do I do this? And one of the things I always say is, when you have a lot of information like this coming at you, indexing your knowledge, organizing your knowledge is key. This is an organizational tool to help you organize a lot of information. Okay. So what we need next, though, since we have bricks, is we need a way to put them together, right? So we need a system or a protocol, a procedure to be able to actually put these monomers together in a stable structure. That's what we're talking about. So when we take a look at the monomer, we have all these monomers, and now what we do is some sort of process to put these guys together into polymers. This process is dehydration synthesis. And so just like it says, dehydration, it involves the loss of water, but it's going to be synthesizing or building your polymer. So let's take a look at how this looks. So first of all, there's an enzyme that's doing this, right? So here I've got some sort of an enzyme that's going to come in here, grab onto these 2 guys. And the first thing it's going to do, so here is my chain, my polymeric chain here, and I've got a monomer here. Now, the first thing the enzyme is going to do is it's going to break this bond right there. It's going to break this bond right there. Now, the second I do that, what have I done to those atoms? Are they happy anymore? No, because I broke their bond, right? That was how they satisfied their octet rule. Now, all of a sudden, nobody's happy. Hydrogen's upset. This OH group, this hydroxyl's upset, right? Who's also upset? The polymer, right? Because it's like, wait. That hydrogen was covering for me, right? We were sharing something there. Now you just took that away. Now I need something again. I need another partner. This guy also, same thing. It's like, wait. That hydroxyl, that had me covered. That had my octet rules covered. Now you just screwed me all up, right? So here's what the enzyme does. The enzyme says, wait, okay, hydrogen, hydroxyl group, relax. Why don't you 2 meet each other and form water? You're nice and happy now, aren't you? Okay, get out. Okay, that's dehydration. But guess what? We're not done yet, are we? You know what, polymer? You're still unhappy. I see that little frowny face on you, right? Monomer, I see you're unhappy too. I see your little frowny face. Guess what? I have a solution for this. Polymer, meet monomer. So now all of a sudden, you link the polymer to the monomer. What was 2 becomes 3. We're all happy again. You want to add another one? Do the same thing. Bring in a 4th. Go through the same process and attach that 4th one. What was 3 becomes 4. 4 becomes 5. 5 becomes 6. As far as you want to go. As big as you want this to go. You can make it as big as you want. Just like your brick wall. If you've got monomers coming in, you can make your brick wall as big as you want. All you need is bricks and a way to put it together, right? So the whole system of mortaring the bricks together is what this is. So dehydration synthesis, in our analogy, is the mortar. You take a monomer, slather with some mortar, you stick another brick on that brick, right? You glue them together, right? You slather some mortar on that one, you stick another brick on there. So the slathering process of mortar is the dehydration synthesis. You're connecting monomers together in a structure. Now, what's the flip side? Let's take it all apart. Now, in some cases, you may want to actually do this. You may want to deconstruct a wall, right? A lot of times you just take a sledgehammer to it, but you might want to salvage some of those bricks, right? You're like, you know what? I want to do something else with those bricks. I don't want a wall here, so I want to cut this wall up. You can do that, right? You can demo it. You can actually cut through the mortar. It's not easy, but you can do that, right? And you can separate and liberate the bricks from each other, clean them up a little bit, and you got your monomers back. And you can do whatever you want with those. Throw them at people or whatever, right? Not necessarily, right? That's just something you could do with it. But what does that mean? That means you need a process to undo what you did. That means you need a process to break it down. That's hydrolysis. So hydrolysis means water. So water, hydro, water. Lysis means to cut. So this actually means to water cut. It's a water cutter. So let's take a look at the hydrolysis process. So hydrolysis process, here you have your polymer. So you have your full polymer. And then what's going to happen is the enzyme, different enzyme, by the way, not the same one. They don't all do the same job. In this case, another enzyme is going to come in. It's going to take water. It's going to split water. Of course, as soon as we do that, what have we done to water? Now it's unhappy, requires resolution, right? We also split this bond right here. Now what have we done? Made these guys unhappy again, right? Frowny faces all the way around. Now this enzyme says, listen, don't worry. Hydrogen, why don't you meet the polymeric chain that's getting shorter? Hydroxyl, why don't you meet the monomer? And then basically what we've done is we've essentially reversed the process and we've popped the monomer off. So now a polymeric chain that was 3 now becomes 2, and you got a free monomer to do with whatever you want. And this could basically go off and do some sort of a biological job. Like energy, for instance. Maybe you need to break this down in order to make energy from it. Okay. So you have a two-way street. Notice the reversibility of the reaction. Dehydration synthesis is the forward. Hydrolysis is the reverse. But notice you tend to use both of them equally, depending on what you need. If you need to build your polymer, forward reaction. If you need to pop off some of those monomers because you need to use them for something, hydrolysis. This is a perfect example of the reversibility of biological reactions. We're all about reversibility. Yeah.
So in this graphic, the one on the left side is the poly, one on the right side is the monomer.
This one,
Yeah.
this will be the polymer. So the polymer is now down to 2, right? And typically it's a lot longer than that. So this is the process, it's the protocol for putting these guys together. As a matter of fact, all of our macromolecules, when we're putting them together from their monomers, are all put together by the same exact reaction, dehydration synthesis. If we tear those molecules apart, it's all done by the exact same chemical reaction, hydrolysis. Okay, so these are 2 very fundamental reactions that are constantly happening in your body all the time. Okay, so now that we've got dehydration and hydrolysis under our belt, that right there will be the cutoff for the exam. The exam will go up to and including the discussion of dehydration and hydrolysis. Okay. Now, exam 2 will begin with carbohydrates. So all 4 of the macromolecules will be on exam 2, plus however farther we get. Okay. So this is our break. This is our clean break. So now let's talk a little bit about carbohydrates. So carbohydrates all have a kind of common ratio to them, right? So it's a 1 to 2 to 1 ratio of carbon, hydrogen, oxygen. We already saw that, didn't we? C6H12O6, you can reduce that to 1 to 2 to 1, right? For every carbon, there's 2 hydrogens and 1 oxygen. And so that's a very common sort of a thing that we see in carbohydrates. The other thing you also know about carbohydrates is they have a lot of carbon hydrogen bonds in them. And of course, what do we know about these carbon hydrogen bonds? They're full of. Oh, nice little cupcake out there. But anyway, I'm coveting people's cupcakes. But this is like, it's like I know it's like upside down. It's like something bad happened to that. I don't know what happened there, but the morning hasn't gone well for that cupcake. But anyway, right? So there are a lot of energy. As a matter of fact, carbohydrates represent your body's preferred energy source, fuel. That's what it prefers to burn. Now, does it burn other things? Yes, we'll talk a little bit more about this when we get to the storage capacity of carbohydrates a little bit further down in the chapter. But basically, these guys have a lot of energy in them, so they're natural fuels for your body. Anybody who's ever worked with sugar, if you've ever like burned sugar, you know that sugar can burn actually quite nicely, quite easily, right? So some examples of this, obviously we have sugar, starch, glucose. Now, just to, I always like to say this, but this term right here, I don't prefer this one. And there's a reason why. This is kind of like an old person word. And I say that respectfully, old person word. I can tell if you've learned your biology from an old person, like somebody who learned their biology in the 60s, by your use of this term. Because this is what we used to say when we didn't know anything, but we know a lot now. And not only that, but I hate this word, right? Because I always like terminology wise. There's a lot of terminology in biology, and biology are hard enough without there being unnecessary layers of complexity and confusion. This represents one of those. Here's an example of what I want to do, and I want to see what you guys bring back. So here's what I want to do. I want you to go somewhere, King Soopers or whatever, and I want you to bring back sugar. What would you come back with? So you go into the baking aisle, you grab the 5-pound bag of sugar. Okay. Anybody else coming back with something different? Brown sugar, slightly different, but still same idea, right? Anything else? Fruits, right? What was the other one? Powdered sugar, right? What? Pasta's got a lot of sugar in it, typically speaking, right? Huh? A cupcake, right? Our friend. We're thinking about your cupcake. We worked the cupcake into lecture there, right? I like that. That's good for him. Right. What else would you come back with? Gatorade, or a lot of those energy drinks, right? Which are basically, they spark you up because they're mostly just the sugar shot. You guys are missing some obvious ones. What? Yeah, candy, any kind of candy, actually, right? Yeah, but rock candy, that's pure sugar, basically. What? Lucky Charms, yeah, there's a lot of sugar in those guys, right? How many of you guys are pancake fans? Yeah, mostly corn syrup in there, right? That's sugar. So, okay, you guys came back with me. You got like an entire grocery store now that you just come back with. That's not helpful for me, right? Because unless I tell you something else, something more qualifying, you don't know what to come back with. I just said, go get me some sugar. You got the 5-pound bag, okay. You got candy, okay. You got syrup, okay. Right, you got some of these other things, fruit, there's a lot of sugar there, okay. But what I didn't tell you is I'm baking cookies. So which one would that I really want you to come back with? The 5-pound bag, right? But what's the problem here? I wasn't specific enough, was I? You know why? Because the term isn't specific enough. I just told you to come back with something sugar, right? Sugars. But there's an awful lot of variations of the sugar theme out there, right? It's kind of like saying, here's what I want you to do. I want you to go introduce yourself to the guy in a tuxedo at a black tie event downtown where there's thousands of guys in a tuxedo. What's your comeback question for me? Yeah, could you clarify that a little bit, please? Because I'm looking around and I see thousands of dudes in tuxedos. I need a little bit more than that, right? So whenever you use the term sugars, it's like you're referring to a specific person usually, but you're not using a specific term. Is there a question? So here's a good example, just a real world one. If I tell somebody and I ask somebody, have you checked your sugars today? What am I asking them? Yeah, I'm usually talking to a diabetic, right? And I'm asking them if they've checked their glucose levels. Well, guess what? I didn't really care about sugars, really, did I? Because like, have you checked your sugars? Like, why would I do that? Right? Which one are you talking about? Are you talking about glucose, galactose, fructose, sucrose, mannose, maltose? Pick one. It's like the black tie event. It's like you've got an entire body full of sugars. Can you be a little more specific, please? So no, in this case, we knew exactly what, we didn't care about sugars. We want to know what your glucose level is. Then in that case, say glucose, because that's what you mean. Oftentimes, I only give this one a break when it's just Joe Average, right? Because Joe Average, for them, glucose and sugars is fine. And if you're a patient, that's okay. But if you're in healthcare or you're in science and you're doing this for a living, if you know you want to know about glucose, then say glucose, because that is the specific term. Don't give me sugars, because I have no clue what you're talking about. Okay, I got two questions about Christopher and Melissa.
What was the, you know, like all the sugar sodas and stuff.
Aspartame? No, that's exactly what happened. Because the idea was, you know, you got too much sugar in sodas, which you do. That's the reason why we drink them, by the way. So if they don't have sugar in there, we tend not to drink it. I mean, ask those like, you know, those sparkling water companies, you know, how close their market share is to Coke. It's not even close, right? I mean, there's a reason for that. And matter of fact, if you take a look at the most popular drinks, like if you do the blind taste test, you can actually, it's not a brand thing. It's like, oh, you prefer Pepsi over Coke. It's like, it has nothing to do with that. It has everything to do. It's like, you can actually predict it by which one has more sugar in it. That's the one that's going to win. And the problem is, of course, that fattens us up because we're just downing a bunch of sugar. And so that's basically where we kicked into non-sugar containing drinks. But Coke was smart because they realized, well, wait a minute, you guys are mammals. You're not going to touch something that doesn't have sugar in it. We know this, right? We know this. This is the reason why they put sugar in everything. They put sugar in stuff that you don't even think sugar should be in. Why? Because they know you're going to eat it more likely, and you're going to eat more of it. So that's a common thing. I mean, we've known this for a long time. You know, marketing does this all the time. If you put sugar in it, you will eat more of it. That's just, we're pretty consistent that way. But yeah, that's what triggered the use of sweeteners, artificial sweeteners and things like that. And aspartame was the original one that came out back in the day. I can't think of any. Yeah. Nobody cares. Nobody cares about all the rest of them, because any of the rest of them, I mean, you might. I mean, if you want to look at like circulating things of that nature, but typically it does eventually. But I mean, but in circulation, that's where you'd go. is, I mean, you got free glucose, but you also have circulating disaccharides that be circulating in your system. But typically speaking, if you're looking for some other type of carbohydrate, they usually have a specific name too, right? So you use their specific name. And you don't use sugars because nobody knows what that means, right? And that's one of those old world words. It's like we know what we're talking about now. And so sometimes I use it, like when we talked about lab, the biological molecules lab, I use the term reducing sugars. That's one where I couldn't get away from because there's multiple different types of carbohydrates that can be reducing in nature. Glucose is one of them, maltose is another one of them. And so that's one of the ones where sugars kind of applies, because we're not so interested in the sugars part of it as much as we are the reducing behavior of that particular carbohydrate. Technically speaking, sugars can almost always be swapped out easily with the word carbohydrate, which is probably a little more accurate. Right? But that's kind of a thing, because I mean, you know, we know we're going after glucose. So all of these technically can be lumped into that general broad category, among other things. Okay, so let's take a look at our monomers, shall we? We're going to study the bricks. Study our bricks first, and then we're going to take a look at putting them together. So our single subunits basically represent our simplest carbohydrate. Notice not our simplest sugar, our simplest carbohydrate. And so generally speaking, we will have in these monosaccharides 6 carbons in our carbohydrate. And of course, glucose is our poster boy, right? So you got those 6 carbons in there. And so that's our poster boy. So this is our kind of marquee player, our poster boy for this one. So what this basically means is this glucose kind of represents the red brick. Usually if I say brick, what's the first thing you think of? What's the first visual in your head? The red brick, right? The classic red brick. That would be glucose. Glucose is the classic red brick of the monosaccharides. However, you also have 2 others, right? So you have fructose, which we talked about before, which is not just an isomer, but it's a structural isomer of glucose. We'll see what that looks like here in just a second in a couple of slides. But then we also have galactose, which is glucose's stereoisomer. So there's a stereoisomer, a non-enantiomeric stereoisomer, by the way, that we see also of glucose. So all of these are monosaccharides. These are the big 3 that we see of these hexameric or hexose carbohydrates, monosaccharides, right? Is glucose, fructose, and galactose. Those are the big 3 that we see a lot. And the reason why this is important that we have all of these, so this would represent like different colored bricks, right? So like maybe fructose is kind of like a whitish colored brick, and galactose is, you know, I remember a tan colored brick or something like that. Different types of bricks. Fructose would represent actually not the classic square brick, but maybe kind of like more of like a trapezoid brick, right? Kind of one where you can kind of do like circular types of patterns with. So that would be like a structural difference, but still in the brick family. And the reason why this is important is because enzymes themselves are specific for their monosaccharide. So for instance, the enzyme that eats on galactose cannot do anything with fructose. The enzyme that works on glucose cannot do anything with galactose. Each one of these guys has its own specific enzyme. And so if you don't have its enzyme, then it can't do anything with the other monomers.
Those enzymes break it down into glucose and whatever else.
Well, like an enzyme that works on glucose, usually if you're going after glucose, you're breaking it down into other molecules, into smaller molecules. So these are 6 carbon molecules. Different types of enzymes will work on glucose. By the way, if you want to know the enzymes that work on glucose, those are in cell respiration, right? So that's in our cell respiration chapter as part of our take-home activities. And so that whole metabolism piece of it is just different enzymes that attack glucose. And they basically will break it down into 3 carbon molecules and things of that nature. So kind of like deconstruct it. And then of course, with that, you kind of wring out the energy that's pent up in glucose itself. But you have different enzymes that are necessary for each of these. So here's basically our 3 major types of sugars. So you'll notice that we're going to see these guys actually throughout the semester. So we'll see 3 carbon carbohydrates, right? This is basically a glyceraldehyde. So you'll see you have your 3 different carbons. Notice that this up here looks like what functional group? Carbon double bonded to oxygen. This would be a aldehyde. Why? Because you got the R group coming into the carbonyl and it terminates in a hydrogen. So that'd be like an aldehyde type group there. We also have 5 carbon carbohydrates. So you can see they look like a home plate. We have ribose and deoxyribose. So this is basically the carbohydrate that's associated with RNA and then DNA respectively. And so you can see they kind of form like a little home plate ring with oxygen in there. We'll take a look at some of those later on as the structure of RNA and DNA. And then of course you got the 6 carbon carbohydrates, of which we just talked about: glucose, fructose, and galactose. So here's your glucose, fructose, and galactose. So when you take a look at these 2 guys, you can see how these guys are structurally isomeric. So you can see same formula. These guys are all C6H12O6, all of them. But you can see how the arrangements of the atoms are different in fructose. So you got home plate versus a hexagon. So it's a completely different structural arrangement of these atoms itself. So that's the reason why it's a structural isomer. Then we take a look at glucose versus galactose. This is your stereoisomer. Okay, let's take a look at this. Now notice it's not a mirror image. So it's not a right-hand, left-hand sort of a thing. It's just it's a spatial thing. So let's take a look at the spatial. One thing to always notice is when you take a look at the glucose, where it forms a hexagonal ring where oxygen is inside the ring as part of the ring structure. But you have molecules that are above the ring and below the ring. So if they're pointed up like this, that means they're pointing above the ring. If they're down, it means they're pointing below the ring. So in galactose, you notice that your hydroxyl groups are up, down, up, up in galactose. In glucose, that orientation is down, down, up, down. The orientation of the hydroxyl groups above and below the ring is what separates galactose from glucose. Notice, not mirror image, but spatially different. That's the reason why they're stereoisomers of each other. By the way, there's a lot of other carbohydrates where all they do is differ in this. And then like carbohydrate biochemistry, which is one of the areas of biochemistry that kind of, I was like, I'm out. I'm not going to be a biochemist. I'm going to go molecular. This is one of those, carbohydrate biochemistry, because there's a whole pantheon of these types of stereoisomers, and all they just differ by the arrangement of the hydroxyl. So there's like up, up, down, 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 up, up, and up, 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 down, and down, 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 up, and up, down, and up, down, up. It's like you just, after a while, and I had to memorize all of them in biochem, right? And so that's where I learned how to hate carbohydrate biochemistry. But the only reason I say that is to just show you that there's more out there. These are the big 3 that we see in biology, right? But that's what we refer to as a stereoisomer. Okay. So the other thing I want to sort of point out, yes, Bella.
Where are the other cart? Oh, well, yeah, in that picture, I guess where are the other carbons?
For galactose?
For any of them, at the angles, I guess.
Yes, they're at the points. All the carbons are at the points. In this case, instead of a zigzag, so each of the point of the cycle is a carbon. So the other thing that I want to show you is a couple of things. This is kind of a little bit of organic chemistry. It helps us to kind of orient ourselves because we do want to kind of get ourselves oriented here. These are all glucose. These are just different views of glucose that we have here in front of us. But what they're showing you is they want to show you how glucose forms its ring, right? So from a linear chain to the ring-like structure. And so that's what they're showing here to you. So they're basically saying that when you kind of have glucose laid out flat like this, and it's kind of long carbon chain, what happens is the oxygen of the carbon 1 will come in and attack carbon 5. So you can see that here. When it does that, there's a displacement that has to happen, right? Because if you think about that, this actually goes this way, right? So this oxygen comes in and attacks, and when it does that, it wants to form a bond with that carbon, between the oxygen and the carbon. Well, there's a problem there, isn't it? That carbon already has 4 bonds, doesn't it? Does it have room for one more? No. So if you're going to form that 5th bond, guess what? Something has to happen with one of the other 4. There's got to be a loser in this crowd. Well, as it turns out, the least disruptive modification of this would be for one of these double bonds of oxygen to dump its electrons back onto the oxygen. That would bring you to 4, right? And that's exactly what happens. So you can see that this oxygen will attack the carbon. These electrons will go back onto the oxygen, and that typically will pick up a hydrogen to kind of fill that octet piece of it. And then what you'll do is you'll form a bond between the oxygen and the carbon. And so notice what you've done. You've created a hydroxyl group. There's a single bond there now with a hydroxyl group associated with it. Now, when you do this, it creates 2 different forms of glucose, alpha versus beta. And all these 2 forms differ is by the orientation of the hydroxyl group above or below the ring. So if your hydroxyl group is below the ring, then you're alpha. If your hydroxyl group is above the ring, then you're a beta. That's it. That's the only difference between alpha and beta glucose. It seems negligible. Are they both glucose? Yes. Do they behave the same? The answer is no. We're going to see some examples of how using alpha versus beta glucose will give you very different outcomes when you're building molecules. Good. You mean like in terms of, no, they form the same, right? So like why are they oriented differently? Like up, down, up, that sort of thing? So those would be on the so for the differences between galactose and glucose, whether the hydroxyls are up or down, is associated with the other carbons, not so much the 1 carbon. The 1 carbon is kind of a special case in the sense that the placement or the orientation of the 1 carbon up or down is defining 2 different glucoses. Technically speaking, you would also have 2 different galactoses in that sense. But what's defining the difference, spatial difference between a glucose is what's happening on carbons 2, 3, 4, and 5. So what's happening around those. But I'm glad you mentioned that, because now it kind of forces us to talk about the elephant in the room, which is these blue numbers, right? So the carbons are not all the same, right? So when we take a look at a carbon chain in organic chemistry, what we realize is that just because you're in a carbon chain doesn't necessarily mean that your reality is the same. Think about it this way. If you live in a neighborhood, your reality in that neighborhood is affected by who's immediately next to you, right? So your reality, the way your life goes as you're living in your neighborhood, is affected by your neighbor on your left and your neighbor on your right and the neighbor across the street. And those 3 will dictate sort of how your reality works. Now, that's not necessarily true for my next door neighbor, because their reality is affected by the person on the other side of them, right? I don't feel that person. I don't interact with that person. So my reality is a little bit different than my neighbor's reality, because that person may be just a flaming a-hole, right? Who's ready to call the police the second that, if you're not out there shoveling in the middle of the heavy snowstorm. It's like, even though you got 24 hours, it's a clear sidewalk, right? So they may be just a real jerk. So that creates a very different reality for your next door neighbor than what you feel, because your next door neighbors may be sweethearts, right? But that's what you feel. So even though we are kind of in the same chain of houses, who we're surrounded by creates very different personalities for us. And we notice that with carbons as well. We notice that when you have carbons in a chain, who you're surrounded by creates different temperaments, if you will, of carbons. So not all carbon realities are the same. And so not only that, but if you're adding functional groups to something, you also need to be able to communicate where you're adding it, right? So if I add, say, for instance, a hydroxyl group to an octane, where am I adding it? I could add it to any one of those 8 carbons. Am I adding it to carbon 1? Maybe. Am I adding it to 2, 3, 4, 5, 6, 7, 8? It could go anywhere. So how do I communicate which one it's on? Well, oftentimes I'll designate a number. I'll say this is 6 octane. What does that mean? I've got a hydroxyl group, or 6 octanol, right? I've got a hydroxyl group on the number 6 carbon. Oh, that's great. It's on the number 6 carbon. Great. How do you know it's not the number 2 carbon? Right? If you count from the other end, it should be 2 octanol, not 6 octanol, right? So how do you know which one's which? How come it's not 2 octanol? Where do you start numbering when you designate who you're bound to? Nope, you know it beforehand, right? So we're in organic chemistry. Remember, we said we have all these functional groups, right? Well, what we didn't say is in organic chemistry, the way they do their nomenclature is they organize these functional groups in priority. And sometimes they do oxidation state and things like that. So stuff that you don't need to know about. But there's a pecking order, right? So there's a high priority functional group, and then there's very low priority functional groups. And if you have a very high priority functional group attached to a carbon, that gets the designation of number 1. As it turns out, carbonyls and carboxylic acids are among the highest priority functional groups. And so what do we have on the top attached to carbon number 1? Carbon number 1 is what? A carbonyl of the aldehyde type, right? So this is a very high priority. So that designates that carbon as number 1, and you start counting from there. Okay. This is the reason why we have this numbering system, because then as we close this system up, we notice that our number 1 carbon is here because that was the old carbonyl carbon, right? Then we just go around. There's number 2, 3, 4, 5, and then 6 is above the ring. Now, what does this do for us? What this does for us is it helps us to orient ourselves. So as 2 different molecules are interacting with each other, it gives us an idea of where on their molecules they're interacting. So are they interacting between their 6 and their 1, between their 1 and their 2, between their 1 and their 4, right? Where are they interacting? So because there's a lot of places on this molecule to kind of do stuff on. So where are you interacting on that molecule? That's what the numbers give us. So whenever you see those big numbered molecules like on pesticides and things like that, where they've got like, 1, 3, 5, 6 tetramethylene, that sort of thing, that 1, 3, 5, 6 is the numbering of the position of where on the carbon backbone they are. And then the word that falls after tetramethyl means that there's 4 methyl groups attached at each one of those carbons, right? So you have 1 at each one of those carbons. So organic nomenclature is very descriptive. It's like a word map of the molecule. Okay. And once you kind of get used to it, actually, it's so much better than inorganic chemistry. But anyway, so this is kind of like our stereoisomer. So we saw the ring structure of our stereoisomer and our structural isomer between glucose, fructose, and galactose. This is the flat version. And this kind of like shows you a little bit about the differences in their structure, right? So if you take a look at it, remember glucose is what's called an aldose, right? It's an aldehyde. So if you notice that all carbohydrates end in the suffix -ose, right? That's a carbohydrate thing. Sucralose, right? That's a carbohydrate. Dextrose, right? Mannose, maltose, glucose, right? Cellulose, those are all carbohydrates because they end in ose. An aldose is a carbohydrate that has this aldehyde function on it. So it's got this aldehyde carbonyl on it. So carbon double bonded with the termination of hydrogen. Now, when you take and notice galactose is also an aldose, but it only differs in its orientation of that hydroxyl group. Okay. So that's why it's a stereoisomer. The structural isomer of fructose, you can see very clearly, right? Because here you have an R group coming in to the carbonyl, an R group going out, which makes this a what? A ketone form. It's a ketose, right? So what we did here structurally is literally the same thing that I did when I did propanol and I made propanone, and then I just moved that little bond over to the end and I made propanal. That's the exact same thing. The only difference is your ketose, fructose, is in the middle of the chain, and your glucose, which is an aldose, is at the end of the chain, that carbonyl. But notice, you can't start numbering at your carbonyl and fructose, can you? Because it's in the middle, right? So the question is, your high priority carbon has to have the lowest possible number, right? So here's your two choices. Let's number fructose. We could either do 1, 2, 3, 4, 5, 6, right? That's one possibility. The other one, we could start up here, 1, 2, 3, 4, 5, 6. So which convention gives the lowest possible number to our highest priority functional group? This guy right here, right? So this is one of the reasons why, when you take a look at your home plate, you have your 2 up here. So here's 6, and here's carbon 1. This is 2, 3, 4, 5. Oops, I kind of missed it there. 4, 5, and then 6. Okay. So that's the reason why you have the numbering convention the way you do for fructose. That's going to come in handy, especially when we start putting this together to start making disaccharides. Okay. And so what we'll do is we'll pick up with disaccharide production. We will do that obviously after the exam. So that'll be next Tuesday's pickup point. So I need to make a bunch of copies.